the chain rule for derivatives, one of our versions of the derivative of a composite function was called f prime of u times the derivative of u. So that's what this part is right there, okay? That's our composite function. That's the f prime of u times the derivative of u. And it's got to work out that way, okay? And as I work some of these, I think it's hard for you to see why it has to work out that way and how it works out until I give you a concrete example. And we're just a couple of minutes away from that. But it's got to work out just like that so that we can write it just like that. Because once we get this, now, f of u has to be a function that we can find the antiderivative of, but then we can take the antiderivative, and I'll show you how to work it all out, okay? So we got yesterday to the general power rule. So if you have an expression of x, okay? Oops, circled the wrong place, didn't I? If you have an expression of x, let's assume for a moment x is the variable of our function, all right? An expression of x with some exponent on it, some constant exponent on it, and du. Then the antiderivative of that works the same way for the u as it did for the x, which is add 1 to the exponent, divide your coefficient by the new exponent, plus c. All right, we have some guidelines on page 299 at the bottom for making a change of variables. So this is called integration by substitution. This is called integration by change of variables. This is called substitution by change of variables. Okay? And once we've done a couple of examples, then I need you to come back to this and read it again. But we're going to choose a substitution. We're going to decide what u equals. And it says usually it is best to choose the inner part of a composite function, such as a quantity raised to a power. Very much like the chain rule for differentiation worked when it was quite often u was a quantity with an exponent on it, wasn't it? Not always, but quite often it was. Same thing is going to be happening here. Sometimes u is going to be a quantity with an exponent on it. Once you've chosen u, then you have to compute du. You have to figure out, u meaning you, have to figure out what du equals. Then you rewrite your integral so that it's a function of u instead of x. If you've done everything correctly, you now have a function of u that you can find the antiderivative of. So you find the antiderivative of that. But it's going to be all in u's. Replace u with what it equaled in terms of x, and then by the time we're done with that, almost nobody does that. Should you do that? Yes, you should. Do as I say. Okay? So, number 8. All right, this is page 304. We're supposed to find the indefinite integral and check the result by differentiation. We're going to find the indefinite integral. We have the integral of x squared minus 9 quantity cubed times 2x dx. Now, according to our guidelines, we will quite often choose a u that is a quantity with an exponent on it. So I see a quantity that has an exponent on it. What quantity has an exponent on it? The x squared minus 9. Now, and it is quantity cubed, but it's the quantity that we need to focus on. So, let u equal x squared minus 9. And if that's what u equals, Here's how you find what du equals. If u equals x squared minus 9, and the directions of the problem said, find the derivative of u, wouldn't you say that the derivative of u, which you can call u prime or you can call du dx, equals, now, what's the derivative of x squared minus 9? Derivative, not antiderivative, 2x. Okay? And then, the benefit of life is this notation, you'd say, okay, I can multiply both sides by dx and get that. Okay? So the notation, we're trying to use it to our advantage. And now we have du equals 2x dx. It's always going to work out that way. You don't have to do this stuff. All right? And in fact, if you want to, you can just think of it as du meaning the derivative of u. And why do we throw in dx at the end? Well, a couple reasons. One, it's an integral. Somehow the dx is always there. And two, you can think of it as a chain rule, 2x times the derivative of x. It would be 1. Let me rephrase that. Take this out of an integral problem, right? Go back 3 or 4 months, the derivative of x would be 1. So it would work, right? You still get 2x for the derivative. So think of it that way, and that works okay. So either way we think about it, we get du to equal 2x dx. Well, look how fortunate we are. We have a 2x dx. Okay? So now we rewrite our original integral to make it in terms of u. So here's what you do. Go ahead and write it down, below, but I'm going to do it out to the side so that you see me doing it, and I'll try to explain my thinking as we go. So the integral sign stays the integral sign. Instead of x squared minus 9, I'm going to put what it's equal to. What is x squared minus 9 equal to? U. So instead of x squared minus 9 cubed, it's u cubed. So look, I've replaced all of that with u cubed because all of that is equal to u cubed. And then look what I've got to do. I've still got a 2x dx. I can't write down 2x dx because now I'm trying to take the antiderivative of something with a u and an x and a dx, and that just doesn't make any sense at all. So replace 2x dx with what it equals, which is du. And so we get the integral of u cubed du. And now, if you want to, just pretend that's your original problem. Because we've done integrals, derivatives, you've done math with lots of variables besides x, haven't you? Well, that's all we're doing here. We're doing an antiderivative. We have a u instead of an x. So, power rule for antiderivatives, add 1 to the exponent, divide your coefficient by that new exponent, plus c. And you should be, at this point, fairly happy with the results. That looks like an answer that we've had in the past, just with a u instead of an x. But our original problem is a function of x. It's an integral in terms of x. Our answer needs to be a function of x in terms of x. So, guess what you did? You substitute again. You replace u with what it equals. And what does u equal? X squared minus 9. So our final answer is 1/4 times the quantity x squared minus 9 to the 4th plus c. That seems like a much simpler problem than all of the theory going on before it, doesn't it? Now, what if they hadn't have put the 2x there? We'd be up the creek. We can't work that integral if that 2x isn't there. Okay? So like I warned you about yesterday, for a while, the authors of the book had to be pretty careful to make these up just right so that we can work them. Okay? We'll get that. If that was a 3x instead of a 2, we can handle that. All right, number 10. Whenever possible, I still want u to be a quantity with an exponent on it. Okay? So, what do you think u ought to equal? 1 minus 2x squared, negative 4x, cube root of 1 minus 2x squared. What do you think u should equal? It's just the quantity. U is the quantity. You're looking for a quantity with an exponent, but then you want u to be that quantity. Now, that's not a rule forever. That's what usually happens. Okay? So we let u equal 1 minus 2x squared. Now we compute du. We figure out what du has to equal. If that's the correct u, then there's only one correct thing for du to equal. So du equals, then you take the derivative of 1 minus 2x squared, and you get negative 4x dx. And now we make the substitution. So the integral sign remains the integral sign. Charlie? No, du is not the integral of u. Du is the derivative of u. Then we'd be up the creek. Then we wouldn't be able to work the problem. Okay? So, cube root of 1 minus 2x squared needs to now be written as cube root of u. I'll get to the 1/3. So, I've replaced, so the integral the integral sign remains the integral sign. The cube root of 1 minus 2x squared is now the cube root of u, and negative 4x dx is now du. I've been teaching calculus for 28 years. I've never called it an integral sign before. Okay. Makes sense? And now, either literally rewrite it or at least think of that as a u to the 1/3. And we can take the antiderivative of that. Use your general power rule. So we add 1 to the exponent. So the new exponent's 4/3. We divide our coefficient by 4/3, which means we multiply it by 3/4 plus c. And we're really happy, but we're not finished. Because our answer is in terms of u, we need to replace u with what it equals. So substitute 1 minus 2x squared back in for u, and now we're finished. Well, no, I don't want you to think of it as throwaway. Let's do this. Let's say this is our problem. The integral of the cube root of 1 minus 2x squared dx. Okay? We don't know how to, that's a composite function, right? And we don't know how to integrate composite functions unless we use substitution. So we would say let u equal 1 minus 2x squared. And if you don't mess with the du, so let's say that we just forgot completely that there needed to be a du, we would rewrite that as the cube root of u dx, which doesn't make any sense. Because now we're saying that this integral is a function of two different variables. It can't be a function of two different variables. It can't be a function of u and a function of x. Okay? So you say, okay, well then just go back up here and you do du equals negative 4x. And maybe you remember a dx, maybe you don't. But the point is, so what? I don't have a negative 4x dx to replace. I can't do a substitution to get rid. You see what I'm saying? It's an incomplete. That's a problem. Now, some of them that we still can't integrate, we will eventually learn methods to take care of, and some we just will never be able to do. So at this point, we would think of that as, hey, that's one we just will never be able to do. Okay? And then that way you'll be happy when we do find ways around some of them. Does that make sense? You lost me. That's possible. And if du equaled 4 dx, and that's what we had there, then we'd be happy about it. If it's not what we have there, then we're kind of sad about it. I guess one point I need to make is, don't think this means we can now find the integral of everything, because we can't. If the du doesn't work out just right to equal what's already in our integrand, then we still can't work the problem. A different by a constant we can usually handle, but the big thing is just think like on this one, if that just weren't there at all, we can't work the problem. Okay. Uh-huh. Right. Constants we can usually handle by factoring or multiplying or whatever we need to do. But we'll get to that. Number 12. All right, what's your guess for u to equal? I'm going to guess x cubed plus 5. And it's an educated guess, but it is a guess. So I'm going to let u equal x cubed plus 5. Now I compute du. So what does du equal? 3x squared dx. So this is the question y'all were just asking. What if it's different by a constant? Yeah, multiply both sides by 1/3. Because look, it's not that we have our heart set on having a du equal to something. What we have our heart set on is being able to replace everything in our integrand. So see, I can replace this, can't I? I can turn that into a u to the 4th. So I need to be able to replace x squared dx with something. What's the derivative of x cubed? So if you multiply both sides of this equation by 1/3, you now have 1/3 du equals x squared dx. So don't get hung up on wanting to have du equal something. We want to be able to replace all of the x's and get nothing but u's and du's. Okay? So we're ready to substitute. So watch this. We have the integral sign. Now, I'm going to concentrate on this. X cubed plus 5 is u, and then since it's x cubed plus 5 to the 4th, u to the 4th. So u to the 4th replaces what I have boxed in green. Now look what I have left to replace. I need to replace x squared dx. Well, fortunately for us, x squared dx is equal to 1/3 du. So I replace x squared dx with 1/3 du. And I'm not all that concerned with the order I write these things down in because it's a multiplication and I can put, factors in any order I want to. So, you with me? Now, let's factor out the constant and put it in front of the integral sign. So, I've got the integral of u to the 4th times 1/3 du. I'm going to factor out the 1/3, put it in front of the integral sign, so I get 1/3 times the integral of u to the 4th du. And now I do the antiderivative. So I have the 1/3 out in front. Then I add 1 to the exponent, make it a u to the 5th. Divide the coefficient by the new exponent. So since I've already got a fraction in the front, multiplying by 1/5 is a little easier than saying I'm going to divide it by 5 plus c. And I need to do two things to be finished. I need to simplify 1/3 times 1/5, and I need to replace u with x cubed plus 5. So my final answer is 1/15 times the quantity x cubed plus 5 to the 5th plus c. No, because think of it this way. Call it C1 there. Distribute the 1/3. Now call it C. Because it's just a constant anyhow. All right, you're starting to see some light. Number 17. We have the integral of 5x times the cube root of 1 minus x squared dx. All right, you've seen what? 3 whole examples? You should be experts by now. What are you going to let u equal? Let it equal the quantity that has the exponent on it. So let u equal 1 minus x squared. We'll pretend that we've guessed correctly. And if u equals 1 minus x squared, what does du equal? Negative 2x dx. And I got to say, I'm just a little bit disappointed. I wanted du to equal 5x dx, didn't I? All right, so let's pause for a moment. We're going to handle it, but let's pause. All right, this can be rewritten as the cube root of u, but I need to be able to replace 5x dx as well. And I'm really close. I have negative 2x dx instead of 5 dx. So what should I multiply both sides by to turn that negative 2? Negative 5 halves. So when you multiply both sides by negative 5 halves, you will now get a positive 5x dx on the right. And on the left, you get whatever you get, which in this case is negative 5 halves du. I don't mind any constant in front of my du, do I? Because once I do the substitution, I'm just going to factor it out anyway. So constants don't bother me. They shouldn't bother you. All right. We're ready to make our substitution. So we've got the integral up. And notice when I make the substitution, I'll worry about the u part first. Okay? So the cube root of 1 minus x squared is equal to the cube root of u. So I'll make that substitution. Now I have to substitute something in for 5x dx. Well, according to what we figured out, 5x dx is equal to negative 5 halves du. And I'm going to do what with the negative 5 halves? So, if you see that you've got a constant that you're going to factor and put in front, you can just write it that way and save yourself a line of paper. I don't care. Most of the time, I'll go ahead and put the constant in front. Okay? Now, before you finish this one, are there any questions on how to make the substitution? Feel like you're getting the hang of it a little bit? All right. So go ahead and finish that problem up. See what you get. I see some looks of triumph. Don't leave off the plus C. Yep. Can't leave off the plus C. Everybody able to come up with the correct answer? All right. Anybody need more time? Number 40. We don't need to forget about slope fields, because one of the many things that I can guarantee you will be on the AP test, slope fields. So, number 40. A differential equation, a point, and a slope field are given. A slope field consists of line segments with slopes given by the differential equation. These line segments give a visual perspective of the directions of the solutions of the differential equation. A. Sketch 2 approximate solutions of the differential equation on the slope field, one of which passes through the given point. Okay, that's easy enough, so let's do that first. So I would do something like, that, then I would clone that, and there's 2 of them. I'd rather, whoa, yeah, I'll do that. And then part B, use integration to find the particular solution of the differential equation and use a graphing utility to graph the solution. Yeah, we'll see about that. All right, so we need to solve the differential equation. So let's review what it means to solve a differential equation. A differential equation is an equation with a derivative in it. And so if you have the derivative of a function, you integrate, because that's the antiderivative, to get the function. So we know that the derivative of y is x squared times x cubed minus 1 quantity squared. So if we take the antiderivative of that, we'll know what y equals. It has been a while. It's been too long. Differential equations have missed us. We have dy dx equals x squared times x cubed minus 1 quantity squared. All right? Then remember how we did this? We would say, hey, let's multiply both sides by dx. So we'd get dy equals x squared times x cubed minus 1 quantity squared dx. Then we say, hey, let's take the integral of both sides. The integral of dy, the integral of the derivative of y is y. So y equals the integral of x squared times the quantity x cubed minus 1 squared dx. Doesn't that look just like what we've been doing? All right, what are you going to let u equal? Let u equal x cubed minus 1. Well, then what does du equal? 3x squared dx. What do you wish du equal? X squared dx. So how do you turn the right side into x squared dx? Multiply by 1/3. Go ahead and do the substitution and see if you get what I get. Do you? All right, let me explain how I got it. I got y equals, because that's the left side of our equation. The integral sign stays the integral sign. Then x cubed minus 1 quantity squared. Since x cubed minus 1 is u, that becomes u squared. And then x squared dx gets replaced by 1/3 du. All right, go ahead and do the integral. So you've got the 1/3 out in front, and then you power rule, add 1 to the exponent, divide the coefficient by the new exponent, plus c, then put it back in terms of x. So 1/3 times 1/3 is 1/9. U is x cubed minus 1, quantity cubed, plus c. And if you recall, that's what we call the general solution of the differential equation. So those two graphs we have up there are each a different solution. Each of those are particular solutions. The c is different. Okay, with different c's gives you different solutions. So that's the general solution. Well, it still has the plus c in. Now, they do want us to get a particular solution. They want us to get the particular solution that has that point on it. What are the coordinates? 1, 0. So that gives us a method to figure out what c equals for that particular solution. Replace x with 1, replace y with 0. So at the point 1, 0, instead of y equals, it's now 0 equals, because I replaced the variable y with the y coordinate, 1/9, and inside the parentheses, instead of that being x cubed minus 1, it's 1 cubed minus 1, because I replaced the letter x with the x coordinate. Well, that gives us a 0 inside the parentheses. When I cube 0, I get 0. 1/9 times 0 is 0. 0 plus c is c. So now I know what c equals. 0. So the particular solution of this differential equation at the point they gave us is y equals 1/9 times x cubed minus 1 quantity cubed. The solution of a differential equation is a function. So that's the function. Okay. Any questions? I think we'll stop there for a bit. We'll say that page 305, 1 through 39 odd will be your assignment. Yeah, that's about 60 problems.